In this tutorial, we're going to take a look at 3 different mathematical induction proofs, and these are all for series formulas. So I've got a series here. This is the series on the left, and want to prove that this is the formula for the sum of this series, no matter what n is. And the little symbolism after the n over 2n plus 1 stands for all n contained in the positive integers. Z is the set of integers, and the plus means we're talking about only the positive integers. And so the first thing to do in a mathematical induction proof is to show that this formula works for the very first case, and the very first positive integer is 1. So when n is 1, and there's 2 ways to evaluate the left side here. LS stands for left side. We can just look at the first term. It's 1 over 1 times 3, which is a third. Or we could use this formula here. If I put 1 in here, 2 times 1 minus 1 is the 1 here. And 2 times 1 plus 1 is the 3 here, and so I get a third. So you can look at the first term or use the general formula. It doesn't matter. And we want to prove that if we take the formula now on the right side and put 1 in place of n, we're going to get the same thing. And so 1 goes here, 1 goes here. We have a 1 in the numerator. 2 times 1 is 2 plus 1 is 3, so we get a third again. And with the fact that those are the same, so that guarantees us that the formula worked for the very first case. If n is 1, then this very first term will give is the same as the formula for the sum of this whole series that only has 1 term. So that's the first step in a mathematical induction proof. The next thing to do is to assume that it's true for some arbitrary integer k. And the reason mathematical induction works is that we're going to prove algebraically. Actually, I'll write this line down and the next one too. Okay, so this red statement here is the statement we're assuming it's true for some arbitrary integer k. So that's why this is k here. This is k here. Instead of n over 2n plus 1, it's k over 2k plus 1. So we're going to assume that this is the sum of this series, and show that no matter what integer k is, that's always going to be true for the very next case. See, we're assuming it's true for k. We're going to show that no matter what k is, it's always true for the next number. And so what that does is that says, well, if n was 1, then it's automatically going to work for 2. And if n was 2, it's always automatically going to work for 3. And because the set of integers, positive integers, is well ordered, which means that you can take any arbitrary positive integer, and there's always a number exactly 1 bigger than it. So this also means that if k was the number 1000, then it's always going to be true for the 1001st case. And if k was 2010, that it's going to be true for 2011 as well. So no matter what k is, it's always going to be true for the next case. That's how the proof works. That's how it actually works. So we're going to assume that this is true and show that no matter what k is, that it's true for the next case. And so notice the difference between these two statements. So this term is the same as this one. See, this is for the very next case, so there'd be 1 more term in the series. So if I put k plus 1 in place of n here, I'm going to actually generate this term here. That's the k plus first term. And I want to show how that works here. See, if I put k plus 1 here, so this is k plus 1 minus 1. See, that's 2k plus 2 minus 1. So that first term, first part of the term, is 2k plus 1. So that's why that's a 2k plus 1. And then if I put k plus 1 here, I would go 2k plus 1 plus that 1 in the end, close bracket. So this would be 2k plus 2 plus that 1. And so that simplifies to 2k plus 3. And that's why we have 2k plus 3 here. So that's just showing you that that is the k plus first term, the one extra term that that this one down here has that this one doesn't. So I'm going to get rid of my marks here. Go back to my arrow. And so since n is k plus 1 here, if we put k plus 1 here, then that's why there's a k plus 1 in the numerator. And if we put k plus 1 here, 2 times k plus 1 simplifies to 2k plus 3. So I'm going to write down this whole left-hand side here. Okay, so that's what I'm going to do up here. So that's that whole series, exactly the same terms that are right here. And my goal is to show that this has to be equal to k plus 1 over 2k plus 3. Now, notice that I changed the colors a bit. The reason I've got the red here is because this much is exactly the same as what's in the induction hypothesis here. See, this series here is exactly what's here. And so the reason I do that, you have to use the induction hypothesis here. And you see, so the induction hypothesis says that that whole series is equal to k over 2k plus 1. So I can substitute in place of all this series k over 2k plus 1. This term here is really just that the k plus first term in the series. So here's my substitution. So I'm going to, in place of that from the induction hypothesis, I'm going to put k over 2k plus 1, and I've got this other term to add to it. So our goal again is to show that this should simplify to k plus 1 over 2k plus 3. Now notice I'm adding two rational expressions. They have a common 2k plus 1 here. This one also has a 2k plus 3 binomial in the denominator. So in order to get a common denominator, I want to multiply this one by 2k plus 3 in the numerator and the denominator. So that's my next step here. So if I expand this out, and I'll write out what this looks like, k times 2k is 2k squared, k times the 3 is 3k, and then we have the plus 1 here. The k isn't multiplied by it. And it's over our common denominator, 2k plus 1, 2k plus 3. Now, we're supposed to be showing that this is equal to k plus 1 over 2k plus 3. So you might guess what the factoring should be, but I'll actually show the factoring, how this simplifies to this. So I got to factor this numerator. So the 2k plus 2k squared plus 3k plus 1. And I do it by decomposition. I want to find two numbers that add to 3 and multiply to 2, which is 2 and 1. So that's why I'm going to change my 3k into 2k and 1k. And so I can common factor out of this a 2k, and then the common factor here is just 1. So there's actually a 1 here. And so we'll get this will factor into k plus 1 and 2k plus 1. So that's how the numerator factors. So in place of this, I'm going to put k plus 1, 2k plus 1. So here's my substitution. That changes into 2k plus 1 and k plus 1. And those 2k plus 1s, numerator and denominator divide out. And so we're just left with k plus 1 over 2k plus 3, which is exactly what we're supposed to show it's equal to. So that means it's true for k plus 1. So algebraically, see, we didn't use specific numbers here for k. I just used the arbitrary integer k. And so algebraically, this must simplify to this, and it doesn't matter what k is. So that means that it's true for any value whatsoever. It doesn't matter if you're talking about 10 terms or 2 billion and 3 terms, it's always going to be true. And so concluding statement, therefore, the sum of this series is n over 2n plus 1 for all n contained in the positive integers. Now I took almost the whole screen to do that, whole page here. There is a shorter way to do these series proofs, and so that's what I'm going to show in the second example. And then the third example is actually the shortest of the three, so I'm going to compare the two, how they look a little bit differently. So basically, before I get into the second example, see, this is actually the sum of the first k terms. This is the sum of the first k plus 1 terms. So that's what I'm going to do different in the second example, and I'll get into that shortly. So here's example 2. So here's our formula here. I want to prove that the series 1 times 4 plus 2 times 5 plus 3 times 6 is equal to plus up to n times n plus 3. So notice this product of numbers that differ by 3 is equal to n times n plus 1 times n plus 5 over 3. So that's my formula I'm trying to prove. That's always going to be the sum of this series. So the very first thing to do is to show it's true for the first case. So the left side of this whole series, when n is 1, simplifies to the very first term, which is 1 times 4, or 4. Now on the right side here, we have this formula n plus 1 n plus 5 over 3. And so I'm saying if I put 1 in place of n, I should get 4 again. So 1 in place of n here, here, and here. So this is going to be 1 times 2 times 6 over 3. So that's 12 divided by 3, which of course is 4. Okay, so it did work out to the same thing, so it is true for the very first case. If we put 1 in place of n, then the sum of this whole series that would have just one term is going to be the right formula. It does give you the same thing as 1 times 4. So here's my induction hypothesis. So instead of writing out 1 times 4 plus 2 times 5 plus 3 times 6 up to k plus 3, I'm going to call that the sum of the first k terms, which is what that would be. So I'm not writing the whole series, just sk stands for the sum of the first k terms. And it should be k plus 1, k plus 5 over 3. I'm putting k in place of n here. And we want to show that the sum formula for the first k plus 1 terms, no matter what k is going to be, if I put k plus 1 in here, that's going to be k plus 1. K plus 1 plus 1 would be k plus 2. And if I put k plus 1 here, k plus 1 plus 5 is k plus 6 over 3 still, of course. So I want to show that if, as long as this is true, that this formula is always going to work. It's always going to be the right sum of that series. So to do these, we use the idea that the sum of the first k plus 1 terms is the sum of the first k terms plus that last term. Okay. And I'm going to go back to the first page for a moment to show what that looks like. So again, this is the sum of, see, this is the sum right after this one. This is the sum of the first k terms, and if I add to that the next term, I get the next sum. And that's actually, again, I'm going to go back here. Okay, this is okay. So you see on this page here, this right here is the sum of the first k terms. And below, see, this is the sum of the first k terms. This is actually term k plus 1. So if I add that sum and this, I get, and what this is over here is the sum of the first k plus 1 term. So this is the next sum after this. See, if I take this sum and add the very next term, I get the next sum. So that's the idea of what I'm doing on the following page. So let's go, there we go, that's where we were. And we'll go back to pointer. Okay, oh right, that's where we were right there. So the sum of the first k plus 1 terms, we're supposed to show that is the sum of the first k plus term k plus 1. So the sum of the first k terms would be, see, the sum of the first k terms from the induction hypothesis is this, k plus 1, k plus 5 over 3. Plus, okay, what's the k plus first term? The k plus first term, so this is the general term formula to find any term. So if I put k plus 1 in place of n here, that's k plus 1, and k plus 1 plus 3 would be k plus 4. So that is the k plus first term. So let's move up here to do the last part of this proof. So our goal here is to show that this, okay, is going to simplify to this. That's the idea. If we can show algebraically that no matter what k is, it's always going to give us this, then we've completed the proof. It's true for the k plus first term. So in order to add these, I want to get a common denominator. So all I actually did here was I multiplied this by 3, top and bottom. So that's what I did right up here. So I now have a common denominator, so I can actually combine these together. I'm not going to just blindly multiply everything together and collect like terms. Again, I'm trying to, looking ahead, I want to show it's equal to this. Notice that k plus 1 is a factor of this, and I have a k plus 1 common factor in these two expressions. So I'm going to factor that k plus 1 out because I don't need to like expand it in and then factor it out afterwards. That would be kind of defeating the purpose. So I'm going to factor it out. So over this 3, I have k plus 5, and over this 3, that's been factored out, so it's 3 times k plus 4. So now I'm going to expand this together. So k times k is k squared. See, k times 5 would be a 5k here. And if I multiply this 3 by this k, I get a 3k. So that's where that 8k comes from. And then 3 times 4 is 12. So that's just all that expanded and simplified. And now, again, I'm trying to show this is equal to what's over here. So I think I should factor this because this is in a factored form. So I want to find two numbers that add to 8, multiply to 12. And those numbers are 2 and 6. So this would factor into k plus 2, k plus 6. And essentially that is the same as what's here. K plus 1, k plus 2, k plus 6 over 3. Let's just write it in exactly the same form. Okay, so that is equivalent to this no matter what k is. So it's true for k plus 1, so then this formula always works. The sum of this series is n plus 1, n plus 5 over 3 for all positive integers. One more example on the third page here. So I've got this sum formula. It's the sum of all the powers of 2. Now 1 is actually power 2. It's 2 to the power of 0. 2 to the first, 2 to the second, 2 to the third. So they're all powers of 2. That's the general term formula. And my formula says that the sum of the powers of 2 from 1 up to whatever power of 2 is going to be 2 to the n minus 1. So it's actually 1 less than 2 to the power of n for all n contained in the positive integers. So the first thing to do is to show that it's true for the very first case. When n is 1, the left side is just 1. And of course, if I put 1 in here, 1 minus 1 is 0. 2 to the power of 0 gives me 1. So the left side is just 1. I want to show on the right side that here's my formula. If I put 1 in here, it's going to give me 1 again. And it does. 2 minus 1 is 1. So it is true for the very first case. So it is true for the very first case. It's true when n is 1. So here's our induction hypothesis. The sum of the first k terms is 2 to the k minus 1. And we want to show that it's true for the first the k plus first sum of terms. So sk plus 1 should be, if I put k plus 1 in here, it would be 2 to the k plus 1 minus 1. So same as the previous page. The sum of the first k plus 1 terms is the previous sum plus that next term, the k plus first term. So the sum of the first k terms from our induction hypothesis is 2 to the k minus 1. So in place of this, I can put 2 to the k minus 1. And the k plus first term, if I put k plus 1 in here to get the k plus first term, this would be 2 to the k plus 1 minus 1, which of course simplifies to 2 to the k. So that simplifies 2 to the k. I did a little rearranging here. I wrote the second and the minus 1 in the end. So again, we're trying to show that this is equal to 2 to the k plus 1 minus subtract 1. That's the idea here. If we can show that no matter what k is, that's always going to be true, then the proof's done. So these two are actually like terms. We could actually think of this 2 to the k plus this other 2 to the k, same thing, is actually 2 to the k's. So they're actually like terms. There's 1 2 to the k, another 1 2 to the k's, there's 2 2 to the k's. And the reason I want to do that is because I can write that 2 as 2 to the first, and I'm actually multiplying two powers with the same base. And so I can actually write this as 2 to the k plus 1. So this is actually the 2 to the k plus 1 part, minus 1. So that is equal to 2 to the k plus 1 minus 1, which is what we're asked to show. So the sum of the first k plus 1 terms is always going to be 2 to the k plus 1 minus 1. So it's true for n equals k plus 1. So the proof is complete. Now I did say earlier that this is one of the shorter proofs. So what I'm going to do here is I'm going to show what this looks like with the whole series thing to do the two different methods. So instead of writing sk plus 1 equals sk plus term k plus 1, you can instead, oh, there's my concluding statement, right? I forgot about that. So this is the induction hypothesis. Instead of sk equals 2 to the k minus 1, we would assume that this is true for some arbitrary integer k. So 1 plus 2 plus 4 plus 8 up to 2 to the k minus 1 is equal to 2 to the k minus 1. So that's our induction hypothesis if you want to write out the whole series and instead of doing this. And so we want to show this true for k plus 1. So for k plus 1, then it would be 1 plus 2 plus 4 plus 8, etc. And the kth term is that one. The k plus first term, if I put k plus 1 in here, then that term will be 2 to the k. So if I put k plus 1 in place of n, and then I have this minus 1 in the end. So notice that those are opposite, so they add to 0. So that's why the kth term, or k plus 1 term, is 2 to the k. So that's where that comes from. This is actually term k. Well, so it's just term k, no minus there. Let's go back to the arrow. So that's the kth term. This is the k plus first term, and I want this is the k plus first step. So if I want to show it's equal to the sum of the first k plus 1 terms, that's why this is 2 to the k plus 1, and of course there's always a subtract 1 in the end here. So using the series method here, I want to show that this is equal to that. So I would start with this whole series here. So the left side is 1 plus 2 plus 4 plus 8 plus up to this and this term. So that's my left side here. And the reason I'm my color coding here again is because this, from the induction hypothesis, that series, exactly the same as what's here, is equal to 2 to the k minus 1. This term here is just that term there. This part here from the induction hypothesis is equal to 2 to the k minus 1. So in place of this, I can substitute that. So there's my, using my induction hypothesis, I can go 2 to the k minus 1 plus the 2 to the k. And so this is actually exactly the same as what we got here, just a little different order, that's all. So I would rewrite it with this term and this term together, the minus 1 in the end. Again, 2 to the k plus 2 to the k is 2 times 2 to the k. And so I put my 1 in here, and then multiplying power is the same base again. I add the exponent, so I get 2 to the k plus 1. So again, it's true for k plus 1. So I can restatement this, or I could write, you may have seen this before in proofs, QED is Latin for, therefore I have proved what I set it to prove out to be true. It's, I think, quod erat demonstrandum is the Latin. I probably killed that Latin, but anyway. So that's the last example. So 3 induction proofs, and that's it.